Hello everyone, and welcome also from my side. My name is Luigi, and today I'm going to talk about how to leverage simulation to develop complex HMI. Before we start, let me thank my colleague Walt Stewart, who helped me with this presentation. This is our agenda for today. We'll start looking at industry trends and related challenges. Then we'll focus on how to develop HMI with model-based design. We will see an automotive example, and we'll wrap up with some conclusion and takeaways. Let's start looking at some of the challenges related to modern HMI development. In all the major industries, increasing customers' expectations are driving the digital transformation of products and services towards intuitive, easy to use, yet powerful applications. For HMI developers and designers, the challenge is to bring together more and more complex functions with rich, intuitive, smartphone-like experience, while at the same time ensure quality, reliability, safety, security, and time to market. So, it's crucial to adopt proper software design processes and tools. For example, modern automotive dashboards are more and more a key element of the driver experience. They have a lot of information to display in coordination with the other onboard systems. This usually involves complex state machines with nested and parallel states, many state transition and conditional decisions. Also, modern dashboards are start learning from the driver behavior to provide a more customized experience. In addition, as many other industrial systems, modern dashboards have to be reliable and meet safety and security requirements. All these challenges require more and more robust software development processes that can enable fast design iteration, structured software testing, and automation. Model-based design has a proven track record to enable agile, high-quality software development in all the major industries, including aerospace and defense, automotive, industrial automation, communication, semiconductors, and many others. Model-based design is a model-centric approach to the development of systems. Rather than relying on physical prototypes or textual specifications, model-based design uses models throughout the entire development cycle. The models include all the components relevant to the system behavior: algorithms, control logic, physical components, and the environment. Once the models are developed, they can be fully simulated and they used to generate code, reports, and other kinds of documentation. The core components of model-based design are system-level and component-level design and simulation, automatic code generation, and continuous test and verification. Now, let's see how model-based design can help the developers of HMIs. When developing an HMI, there are two typical roles: a developer, who is mainly in charge of the control logic of the HMI, and the designer, who is in charge of the user interface design. An important step is the formal definition of the interfaces between the two worlds, as early as possible in the process. Working with graphical models can help in having a clear and not ambiguous definition of the interfaces, so that parallel development can start. And so, a collaborative workflow can be then applied, where the developer can use MATLAB and Simulink to develop the control logic, and the designer can work on the UI using Qt Design Studio. MathWorks and the Qt company are working together to integrate and expand this workflow, including code simulation and code generation, as we will see in the following slides. Now let's take a closer look at the HMI development workflow. At the beginning of the development, the UI designer and the software development can work in parallel, based on the common interface definition. And with Simulink, the software developer can create the logic and use visualization tools such as graphs and meters so it can visually verify the behavior of the control logic. In Simulink, other tools are also available to make sure that design is robust and meets the requirements. Once the control logic and the UI design are both available, it's then possible to use the integration between Simulink and Qt to enable a co-simulation and so verify the behavior of the control logic in closed loop with the UI design. And when the system has been simulated and behaves as expected, a very important feature in Simulink is the ability to automatically generate production quality code that can be integrated in the Qt application and deployed to the target platform. If you have to design data flow control application, you can leverage the Simulink platform to quickly build your algorithm by drag and drop operation and pre-built function from a huge list of block libraries. There are libraries for different application domains, including the ability to incorporate machine learning and deep learning into your business logic. A key feature is simulation. To verify your design, you can simulate your models, providing inputs and visualizing and logging the results with intuitive tools. You can even enable step-by-step debugging if needed. And from the model of your control logic, you can also generate production quality code. If your business logic requires to handle state, decisions, and transition, you can work with Stateflow. Stateflow provides a graphical environment to design complex, sequential, and parallel state diagrams, flowcharts, state transition tables, and truth tables. Again, you can simulate your logic. Graphical animations enable you to analyze and debug your logic while it's executing. And Stateflow is fully integrated with Simulink, so you can mix the two approaches, data flow and state-driven, if required by your application. Last but not least, you can automatically generate production code from your state machines. In case of mission-critical or safety-critical applications, simulation alone might be not sufficient to assess the functional behavior in all the operating conditions and to ensure the software quality required by industry standards. So, in Simulink, you can complement simulation with static analysis of your models to enforce modeling rules and detect design errors like division by zero and overflow thanks to formal verification. And in addition, you can create structured test activities by adding traceability between test and requirement, running batch testing, and measuring the coverage of your test. And after the control logic and the UI design have been developed and verified as a standalone components, it's now time to verify how the logic and the UI work together. In this example, consider an application that changes the display contents and provides multiple lists of operations to be selected by the user. The Qt company and MathWorks have provided a dedicated Simulink library and a specific plugin in Qt Designer that enable the business logic in Simulink to be simulated with the Qt UI. The data binding is done through the Qt property system. In the Simulink simulation on the left, UI operations such as display switching and movement between menus are received from Qt, and things like display commands and states are sent back to the Qt application. And here is an example of the business logic implemented with the Qt block set. The identifier for each block is the Qt property name to be sent and received by the Qt or QML application. And the core of the business logic is at the center in the purple block. Inside this block, there is this state flowchart that manages the display state transitions. Let's see this example in action. First, start the Qt side application. Then, you can run the simulation of your Simulink model, and because they are connected to each other, you can change, for example, the vehicle speed from Simulink and verify the proper update in Qt. The red block here manages the screen state transition, so let's take a look at inside. And when you operate the UI from the Qt side, you can see that the animation of the state transition in state flow, according to the command received from Qt. And as a last step, once you have simulated and verified the correct integration of the control logic and the UI design, you can automatically generate production quality C and C++ code from the control logics that can be integrated together with the Qt application in your target platform. And as a part of the collaboration between the Qt company and MathWorks, additional work is going on to enable an even more seamless and automatic integration of Simulink code in the Qt Ultralight framework for embedded applications. Now, let's have a look at a more complex automotive example. So far, we've seen how easily you can integrate Simulink and Qt to leverage early verification of your system. Simulink, in addition to provide a full set of capabilities for modeling, simulation and testing, can also integrate models coming from different tools and environments to build a larger system simulation. As an example, this is an automotive application that integrates a Qt dashboard, MATLAB Simulink, and the Unreal Engine for a full system simulation. This application implements a lane departure warning system. This is a system that warns the driver if he is crossing the continuous line. And to detect lane departure, we can acquire the road images from the Unreal Engine and perform image processes in Simulink. The vehicle is controlled using an external steering wheel. The steering, the accelerator, and brake signals are the input to the vehicle model in Simulink. The dynamic behavior of the vehicle is modeled in Simulink, and it's used to calculate the vehicle speed, vehicle position, engine speed that are exchanged within the Unreal Engine and with the Qt dashboard. Of course, in Simulink, we have designed the algorithm to detect the lane departure, taking into account the lane images and the vehicle position. The dashboard on the Qt side was created based on the example included with Qt Creator. The Qt dashboard receives the calculation results from the Simulink and displays the speed, engine speed, and the lane departure warning indicator. And if you are curious, this is how the model looks like. You have this blue block that acquires the road image from the Unreal Engine and feed it into the main controller, the first red block. The controller block performs image processes, handle the steering signals, and detect the lane change to issue the lane departure warning. The other red block is the vehicle model that calculates the vehicle speed and the position that are sent to the Unreal Engine and to the dashboards. The green blocks on the bottom right are used to collect the vehicle information from the other blocks and send it to the Qt dashboard. This is how the actual setup will look like. This is the live demonstration of this application. You see the live image processing in the upper left, the 3D simulation in the upper right, and then the steering, the Qt dashboard, and information calculated by Simulink. You see that the image processing and lane detection algorithm continuously detect the road line. It's that solid white indication. The vehicle dynamics are calculated, so the vehicle speed and the engine speed are sent to the Unreal Engine. And when the vehicle gets close or cross the line, the warning red light is turned on into the Qt dashboard. Okay, this brings us to our conclusions. You have seen how efficient processes and powerful development tools are more and more needed to design and develop modern HMI and user experience. Simulation is a key step into this process, since it enables early verification of your system. You can use model-based design to develop your business logic with Simulink and Stateflow, and use the Qt Simulink integration to co-simulate the logic and the HMI. Last but not least, once you gain confidence in your design through simulation, static and dynamic analysis, you can generate the code from the Simulink model to be integrated into your target platform. Of course, if you like to learn more, there are many resources available. Feel free to visit our booth at this conference and to visit the Matter website, where you'll find all the information related to the Qt Simulink integration and to model-based design. And please reach out to us for any question. We'll be happy to help. Okay, thank you very much for your attention.